Introduction of power electronics. Here I am going to discuss about why power electronics, what are the applications of power electronics, what are the advantages and disadvantages of power electronics, and I am also going to explain about SCR, that is silicon controlled rectifier. Let us take the why power electronics. I am taking the example of coal. Before going to that, you know that in our India, our energy scenario in India is most of the energy which is generated is all about from fossil fuel, that is 87 percentage. In that 70 percentage is from thermal and 6 percentage is from nuclear, and rest of the power is generated from renewable devices, renewable resources, that is like solar, wind, ocean, etc. And the thing is, we are expecting that uranium is going to last for 50 years, oil is going to last for 100 years, natural gas is last for 150 years, and coal is going to last for 200 years. And after that, we don't know what actually happens. Okay, but the thing is, civilization is not going to end, no? So we need to, in order to protect all these things, what you have to do? So here, in order to protect these devices, let us take the example of one thermal one. In that thermal, I am taking coal as example. Suppose if you want to generate the power from coal, here fuel I am taking as coal. Okay, fuel as coal here. So when you are burning this, you are going to get the steam, no? So only 65 percentage is available at the turbine side, and the output, that means when it is going to the generator side, it is only available as 35 percentage. That means again you need to convert the, that means generator, what it will do, it converts mechanical energy into electrical energy. Here generator is going to convert mechanical energy. That means again there will be some loss of energy. After that electrical energy, it is going to transmitted over long distances, and finally to the substation or to the loads which we are utilizing now for the industrial and domestic applications. Only 16.5 percentage of energy is available. That means if you take this block diagram I have taken here, suppose if I want to generate a 16.5 kilowatt of energy, that means here I have taken 100 kilowatts of, that means for power generation. Suppose if I want to generate 100 kilowatts, only the available power is 16.5. By taking that example, you can see that 16.5 into 6 to 1, no? Approximately if you multiply with 6, you are going to get 100. That means this, for generating 1 kilowatt of energy, you are going to waste 6 kilowatts of that one. That means resources. So like that, what actually happens is, if you are wasting this much of resources, so it may last only up to these many years, but the thing is civilization is not going to end. That means future is available, no? Like our kids or future kids. Okay, for that purpose, what we have to do is, you need to improve that. That means you have to increase these resources for further extension. So in order to make that, what we are doing is, we are going to, that means we need to increase the efficiency. That means here it is, we are getting only 16.5 percentage, no? That means efficiency is very much lower, no? So we need to improve this efficiency. How to improve the efficiency means, here in the place of this, we need to use the power electronic devices. That means by using this power electronic devices, the losses will be less compared to that one. So by making use of this power electronic devices, efficiency is improved, and that is the one case. And another case is, by making use of this renewable resources, we can increase the extension of these resources like uranium or oil, natural gas, etc. So that is the case. One second. Okay, suppose you can see that, why I'm taking one example. Here I'm having one machine. This machine is rotating at 1000 rpm. So I have given the input as 200 volts. Now the thing is, I want to reduce the speed to 500 rpm. So if I want to reduce the speed to 500 rpm, but actually the thing is here 200 is applied means around brush your, this is the brushes. So these are the brushes. You can see this one and this one. These are the brushes. You will be having around 2 volts of drop. Remaining 198 volts is applied at the machine. So it is rotating at 1000 rpm. But the thing is, I want to change the speed from 1000 to 500 rpm. So if I want to change speed from 1000 to 500 rpm, here the formula for EMF is, you know that the generated EMF is NP pi Z by 60A. So clearly we know that here the EMF is, that means voltage generated is directly proportional to speed. Suppose if I want to reduce the speed from 1000 to 500, here I want to reduce the voltage 198, that means half of the voltage. Then only, because it is speed is 500 means half I want to make, no, actually the available voltage is what, 198. That means I want to make 99 volts. So 99 volts is we are going to give, we have to give. That means here the input I'm not going to change, no, the input is 200, but the thing is I want to change that from 198 to 99. So in this scenario 198 to 199, so remaining 101 volts where it is applying, the 101 volts is going to going, that means we have to 101 by placing the external resistance, we are going to get the 101 volts is appeared at some external resistance. But the thing is, by taking like that, what actually happens, you can see that the voltage drop is 101. So power loss formula is V square by R, no. So 101 into 101 by that particular resistor. That means the losses are more because of the use of resistor. By using resistor, we can decrease the speed, but the thing is the losses are more. So due to power loss at resistor, we can see that efficiency is very much reduced. So that is why what we do is, in the place of resistor, I am going to use the power electronic device. So if I going to use the power electronic device, the efficiency is improved. That means on state voltage drop is reduced. That means from 101 to some value. So because of that value, so we can control the speed. I will take you one example now. You will be clearly knowing. Let us take one example. In every house we are using fans, no, we are using fans. So previously we used that fan regulator. This is the fan regulator. You can see this is the fan regulator. Now presently we are using fan regulator, this one, that is triac based. So here you can see that the previously, that means in order to change the speed, what we are having, the size of this device is more, because there we are having the series of resistors. So series of resistor 1, 2, 3, 4, 5. Okay, the 5 positions are there. By changing that position, we can change the speed of the machine. So previously already I told you one example, no, 101 volts is wasted at the resistor, remaining 99 is available at the motor. So that, like that efficiency, that means by using this resistive drop, the losses are more. So by making use of this resistor, there will be that will be power loss, that is V square by R. We know that power P is equal to V square by R, or P is equal to VI. So in the, how we got, so I is replaced by V by R, V by R into V is V square by R. So this is the power loss. So likewise power loss is more. If power loss is more means, that means heat loss is more, means heat sink requirement is there, because heat is more, no, power loss is nothing but heat loss. So because of that, some heat sink is required. If heat sink is required means size of that regulator is also increased. So in order to minimize that, what we are doing, just simply we are replacing this fan regulator by track based one. So you can see this power electronic device. So simply it is a power electronic device. Because of this device, what actually happens is loss is reduced, because no heat sink requirement. Okay, no heat sink is requirement. So if no heat sink is requirement and no resistors are placed, that many resistors, so efficiency is improved. And also no heat sink is now, because of that size is also reduced. So that is the thing. That is why we are using the power electronic devices in order to improve the efficiency. Okay, so that is the reason we are going to learn about power electronics. So what actually happens here, from source to load, you can see that from source to load, here power is delivered to the load. But the thing is, power processing is there, no control action is going to take place. No, just now I have taken fan regulator, no. So by changing that fan knob, we can change the speed of the machine. So likewise, we can change the voltage, or we can change the frequency, or we can change the current. That means here simply we can say that it will going to convert, it is going to convert. That means AC power is going to convert to DC, or DC to AC, or DC to DC, or fixed DC to variable DC, fixed AC to variable AC. So likewise, we can convert from one, okay, one voltage to another voltage levels. So to control and convert the flow of energy from source to load, that is the thing. And finally, we can say that here we one processing unit is there, no, in order to control that one. So that is the reason we are having the power electronics is nothing but control plus conversion, control and conversion. So clearly we can say control is nothing but we can change the voltage level, frequency and current, and conversion is nothing but from AC to DC or DC to AC or something, vice versa. Okay, so by making use of these devices, efficiency is improved, heat sink requirement is less. So these are the advantages. Okay, I think it is clear now. Now coming to the advantages, because previously we have taken no rotational losses, static device, just we are changing that positions. So no rotational losses, higher efficiency, just now we discussed, because of that heat sink requirement is not there, all those things, higher efficiency is available. Okay, heat sink, less heat. So cooling, less heat means cooling requirement is also less, it is required. So size of the device, whatever the device is there, it is very less. That means compact in size. Only thing is disadvantage is harmonics, because due to switching, when you are going to switch that one, some harmonics are introduced into the system. Okay, so in order to reduce that harmonics, what you have to do, again we need to take the filters so that harmonics will be eliminated. Now coming to basic device in the thyristor family, we are going to discuss about the silicon controlled rectifier. So in the silicon controlled rectifier, we know that already diode, we know that in the diode we are having anode, cathode, and extra element is there here, that is a gate. So what is the use of gate? I will explain you in this modes of operation. That is the third mode, you are going to know the main usage of gate. So here it is a, we know that just like a diode here, but it is a two PN junction diodes, PN and PN. That means SCR is having four layers, that is PN, PN, and three junctions. Between P and N, one junction is formed, that is a depletion layer. So N and P, one junction, that is J2, and NP and N, J3. Anode, cathode, and gate. That means it is a four-layered, three-terminal device. So here this SCR can be operated in three modes of operation. One is reverse blocking mode, forward blocking mode, forward conducting mode. We will discuss one by one. Now coming to the reverse blocking mode. So what is reverse blocking mode? We will see that reverse, we know that reverse bias, no, under reverse bias it is acting like open circuit, no, diode. So likewise, reverse bias means P type is connected with negative terminal, N type is connected with positive terminal. So you can see this J1, you can see that J1 here, how J1 is connected, this P is connected with negative and N is connected with positive. So if it is connected like that, it is acting like open circuit. And you can see that J2, this negative is connected with N and positive is connected with P. That is why it is made short circuit. And coming to J3, positive is connected with N. That means negative open circuit only, no, and negative is connected with P. That is open circuit. So because of open circuit, what is the current? Current is zero. So you can see that that's why it is in blocking mode. This one is the blocking mode. So this one is the blocking mode, you can see. So if you increase the voltage, sorry, this is the reverse one, no, reverse one means this one is the third case, because I have applied negative to P type, no. So this is the negative means reverse, this is the third quadrant characteristics, sorry, one. Okay, reverse, this is the blocking mode region, reverse blocking mode. And if I want to increase that current, suppose if I want to if you want to break this depletion width, that means if I want to make the short circuit, if I want to increase the current, what I am doing, I am keep on increasing that one, increasing this voltage. If I keep on increase the voltage, J1 gets short circuited and J3 is also get short circuited. If it is get short circuited, voltage drop is reduced to zero. Okay, so here what actually happens when it is short circuited means a heavy current will be flowing. So this is not safe operating in negative, okay, negative values. In negative values, it is not going to operate in safe. So that is why we are never going to operate in reverse bias case, because it is taking huge amount of current. Okay, so this is the thing. Now coming to another mode of operation, let us go with forward blocking mode. So just like previous one, here the thing is J1 is connected with positive. Okay, and this means P is connected with positive, N is connected with negative. So it is forward bias, means short circuited. J1 is short circuit. Similarly, you can see that J2, N is connected with positive and P is connected with negative. So N and positive means open circuit. That's why it is replaced by open circuit. Now here you can see J3, P is connected with positive and N is connected with negative. That means short circuit. So you can see that here also it is open circuit only, because J2 is open. That means current is 0. So in this case also there is no current flow. So that is the reason you are going to get forward blocking mode only. But the thing is, after some time, if you want to make the short circuit, if I'm keep on increasing the voltage, at some stage breakover takes place. That means here when it is become short circuit, that means this J2 is replaced by short circuit. If it is replaced by short circuit, voltage drop will be reduced. That is why here you can see that voltage here it is coming at this picture. Okay, voltage is coming. That means because of breakover, it is coming to this position, and short circuit takes place. No, huge amount of current will be flowing in that path. So that is the reason here always don't operate in breakover modes. And if you want to on that device before the breakover voltage, that is the reason we are going to operate in forward conducting mode. Let us take that third one, forward conduction mode. In order to, so we have finished with the two modes. One is forward blocking. You can see this is forward blocking and this is reverse blocking. And now conduction mode means you can see that either this one or either this one or either this one. We will see one by one. Now here what actually happens, I am going to connect a gate terminal to this P device. So just now we have got that J1, J2 and J3. J1 and J3 are forward bias. No, in the forward blocking mode, we got short circuit here, and open circuit here. But the thing is, by introduction of this gate, that means a pulse is, that means extra voltage I am going to apply here. So here you can see that there is an open circuit, means charge accumulation is going to take place like this, positive and negative. So it is just behaving like capacitor. Open circuit, no, capacitor. It is behaving like capacitor. So what I am doing, I am introducing the gate so that some current will be introduced into this picture, so that it is going to neutralize whatever the current is there. It is going to neutralize this charge, so that it will become short circuit. J2 will get short circuited. So based upon the short, that means here if gate current is more, means the time interval will be lesser. So that is the reason you can observe that Ig1, Ig2, Ig3. Suppose if it is 4 amps, let us assume that it is 4 amps, 3 amp, 4 amps. Here it is 6 amps. Here it is 5 amps. Okay, if I get more current, means it starts very fast, like this conduction takes place. Suppose 5 amps means it is like it is starting at somewhere that point. So likewise, that means here this whatever the open circuit is there, we need to minimize that one, so that conduction is taking place at very faster time based upon the gate current. That means it is going to trigger. If we trigger, that means previously the gate current is 0, but in this conduction mode, conducting only, no, current is conducting, means in this conduction mode, gate current, as gate current is more, means conducting time will be very faster. So that means anode voltage, anode to cathode is greater than 0, and gate current is not 0. So this is the forward conducting mode. So here you are having again two currents, no, latching current and holding current. You can see this position point N, here it is termed as IL, and below which one arrow mark is there, this is holding current. So definitions two have given here. One is latching current, another one is holding current. So latch is nothing but to turn on. Latch is nothing but to turn on. Latching current, that means to turn on the SCR, minimum anode current to turn on the SCR. So here it is going to turn on, no? That means conduction mode it is taking place, no? So that is why it is latching current. What is meant by holding current? So here this is the, already we observed that it is a blocking mode, no? That means below which, okay, maximum amount of anode current it is, below which SCR will not going to operate. So you already in this, it is in reverse block, forward blocking mode, no? Below which it is not going to operate. So that is the thing. So always latching current is greater than holding current. So these are the definitions which are important. Okay, I think it is clear, everybody. It is cleared. One second. So what you have discussed till now? Okay, what actually happening here? Harmonics. The disadvantage already I told you, no? Harmonics. Why harmonics? Harmonics because by using power electronic devices, here control and conversion is taking place. No, we know that the SCR, all these PN junction diodes, no, it is not going to operate at zero time. So it is because depletion width is there, no. So if you give input voltage as sinusoidal, but we are not going to get the sinusoidal because these electronic devices will not be having some depletion width, so that it is not going to conduct immediately. So that is the reason we are getting non-sinusoidal, but it is a periodic. So that's why it is not operated here, no, non-sinusoidal. So in order to make that, what we have to do, filters are introduced so that it is going to make sinusoidal. So that is the reason. So what actually harmonics here? Why it is undesirable? Because RMS current is increases, and RMS current is increases means I square R losses are also increased, because copper loss is nothing but I square R. And if current is more means power factor is going to be decreases. So that is the reason we need to use filters. So coming to the summary point, why power electronics is needed? Because by making use of this power electronics, efficiency is improved. That is the reason. So that is why we are introduced power electronic devices, and we have seen some applications like track based applications. We can also use in battery charging kit, okay, like washing machine also. So many applications like satellite, in the satellites also for power supplies. So many advantages applications are there. Coming to advantages already told you, by making use of these power electronic devices, heat sink requirement is less, size will be reduced. Okay, so that is the reason. Only disadvantage is harmonics, and also I have discussed about SCR. Okay, so up to here it is harmonic analysis. I didn't, only SCR. What is SCR I have explained. Okay, thank you all of you.